With its vertiginous 700-meter cliffs, its centuries-old villages clinging to the mountainside, and the shades of emerald green from which it takes its name, the Verdon is one of the most visited regions in France. 4.5 million tourists flock to the gorges every year. The Martel Trail alone, which crosses part of the canyon, welcomes more than 1,000 people every day in summer. But behind the famous picture postcard scenery lies an incredible, less-known human technical and geological adventure.
It's extremely rare to have a cut in the rocks of this type over so many kilometers at this height. Few landscapes are as remarkable and as emblematic.
The steep and dangerous relief created from clash of water and stone has not deterred people from settling here. But taming this raging torrent and reaping the benefits has always challenged residents and continues today.
People in Provence have been trying for centuries to domesticate this water, which is a shared, precious, but all too often rare commodity.
The water of the Verdon is essential because, as we say, water is life. The water of the Verdon is the very essence of Provence. So it really is a fabulous thing, a hugely important resource.
Water, the Verdon Gorge's precious but poorly distributed gift, has inspired increasingly cutting-edge ways to transport and store it, so it can serve more people. Since the 19th century, complex canal systems such as the Canal du Verdon have carried water south over more than 80 kilometers. Later, gigantic dams, some reaching 100 meters high, spawned huge artificial lakes, such as Sainte-Croix, the fourth largest lake in France. The project has completely changed the face of what was one of the driest regions in the country.
It's quite a shock. You start off with a large, fertile valley, then all of a sudden you have a massive lake, some 90 meters deep.
The construction of these imposing dams took a great deal of ingenuity. 50 years of toil brought Provence the largest drinking water reservoir in Europe.
Thanks to some major construction work, 1 billion cubic meters of water can now be stored in the Verdon, allowing it to be harnessed for a range of uses: renewable energy, drinking water, agriculture, industry, tourism, all this while ensuring the preservation of the environment and biodiversity.
Come explore the Verdon Gorge. From the formation of the second largest canyon in the world, right up to its most recent hydroelectric developments. Witness how 5 dams have harnessed the region's power without harming its magnificence, taming nature while distributing its riches. Regulating, preserving, and sharing. These are the key challenges of the Verdon Gorge. Carved out thousands of years ago in southeast France, the River Verdon forms a natural border between the departments of Alpes-de-Haute-Provence and the Var. The river has its source in the Trois-Évêchés Massif at an altitude of 2,819 meters, near the famous Col d'Alos. It then runs for 175 kilometers through no less than 32 towns and villages before finally merging with the Durance. Along the 21-kilometer stretch between Castellane and the Lac de Sainte-Croix, over many thousands of years, the river forced its way through the limestone relief, carving out a deep path. The result is the Verdon Gorge, the largest canyon in Europe. The dimensions of the gorge are extraordinary. Made up of limestone cliffs that can rise up to 700 meters above the river, its width varies from 6 to 100 meters at water level, while at the top of the gorge, between 100 and 1,500 meters separates each of the canyon walls. On approaching the Verdon Gorge, it is difficult not to be gripped by the beauty and strangeness of the sight. It's a wonder how nature managed to shape such a landscape, and incredible how long it took.
These rocks are 150 million years old. We can see lots of little fossils coming out in relief, which are corals. It might seem strange to be talking about the sea, given that we are standing at the roadside at an altitude of almost 1,000 meters. That's because of the history of the Alps, where this ancient seabed emerged. We know that Africa and Europe came closer together, and all the sediment that had been gently deposited on the seabed was crushed. So if I were to take a piece of paper to illustrate the sediment at the bottom of the sea, it became deformed by the movement of tectonic plates coming together and began to form reliefs.
This is what gives the Verdon Gorge, halfway between the Alps and the Mediterranean, its fantastic appearance. About 200 million years ago, during the Jurassic era, the whole of Provence was covered by a sea that rose up to where the city of Lyon is today. Over a period of many thousands of years, layers of limestone were deposited on the seabed, reaching a thickness of 300 meters. During the Tertiary era, 100 million years ago, major tectonic movements gave rise to the Alps. This created fissures in the limestone bed. Thrust together, the layers of sediment were then superimposed on top of one another. In some places, several strata overlap, sometimes creating elevations more than 700 meters high. During the same period, the level of the Mediterranean Sea rose and fell dramatically on several occasions. Like all rivers, which naturally flow down to the sea, the Verdon had to find a way through this new emerging relief to reach zero altitude.
We don't often think about it, but we use pressurized water to cut rocks. This means that if a mass of rock rises, and the river wants to reach sea level quickly, the more it rises, the greater the speed of the river, and the faster the incision through the rock that has been broken and deformed by tectonic forces. The water seeps into the cracks in the rock to cut a way through and flow straight down.
To visit the Verdon is to contemplate a landscape shaped by water over a period of more than 40 million years. As it dug its bed, this tumultuous torrent created a majestic relief. It is nevertheless extremely dangerous and difficult for man to access. Even today, many areas of the river are accessible only by water. However, this complex topography has hindered rather than completely prevented the development of human activity.
The Verdon landscapes are very austere. In spite of everything, man has always tried to tame this mineral universe living here and create paths along the cliffs. Humans have managed to adapt to this harsh, sometimes austere, sometimes hostile environment.
Humans were able to settle here because there is a supply of water. Plus, there are animals in abundance, so they could live by fishing, hunting, and taking shelter in caves. The area had everything they needed.
Since prehistoric times, man has been living in the cavities hewn out of the rock by the water.
The caves we see on both sides of the river have been occupied since time immemorial by man, with the earliest occupations dating back some 100,000 years. This is the Middle Paleolithic. Man could live in these caves sheltered from the cold. While the whole of northern Europe was under ice, this part was preserved.
But even then, man first had to domesticate the Verdon. Although viewed from the river's edge, the water may seem beautiful and welcoming. Remember that the Verdon was at one stage a veritable torrent, subject to capricious currents. These dangerous rapids can easily drag a bather beneath the cliffs, into underwater caves or under huge rocks, with the suction phenomena leaving no hope of escape. Swimming is thus prohibited in certain sections, in spite of the various developments that have taken place in the Verdon since man first settled here.
This scenery has changed a great deal since prehistoric times. The tumultuous raging torrent is now rather calm and quiet. But the river has its inherent dangers. Some of the caves have become submerged. Prehistoric man would not recognize this place as the same one they lived in several 100,000 years ago.
During antiquity and in the early Middle Ages, small villages linked by mule tracks began to appear along the Verdon. While access and trade were difficult, it did not prevent the development of a flourishing activity. The ceramics village of Moustier-Sainte-Marie is a perfect example.
Human settlement in Moustier dates back to the 5th century. Monks from the Lérins Abbey came to evangelize this part of Provence, settling in the caves overlooking the village of Moustier. The location is not very suitable for construction. During the construction of Moustier, adjustments had to be made to accommodate the limestone rock and the slope of the terrain. The monks began by clearing the lower part of the village to create fields before erecting the earliest religious monuments around which the very first houses of the village were built.
Here, the infrastructure defies gravity by clinging to the edges of the cliffs. Standing almost 400 meters high, these cliffs form a natural barrier to the north. To the south, the village is protected by ramparts built into the rock face. In order to accommodate any faults or weaknesses in the rock, these fortified paths are fitted with arches to allow better load-bearing distribution. Buttresses were also erected along some of the steep slopes to provide better stability for the village's upper terrace.
The village rests on a tough terrace, a rocky concretion naturally occurring in the Verdon. So, to support the weight of all the constructions made through the centuries, we have discharging arches, notably beneath the Moustier road bridge. The village has had to tame the relief of the Verdon landscape.
Not only its relief, but also its waterways. In addition to being perched at an altitude of some 650 meters, the village of Moustier-Sainte-Marie is crossed by one of the Verdon's tributaries, the Adoux. The exact location of the source of this watercourse is unknown, but it has been supplying the city for more than 15 centuries.
This water is a valuable resource and has been of huge benefit in the economic development of Moustier. Starting in 1893, Moustier was one of the first villages to benefit from electricity. We have a hydroelectric plant in the village which allowed inhabitants to be supplied with electricity, thanks to the water.
But not every town in the area is lucky enough to have a natural spring on their doorstep. The 19th century brought new requirements. The expanding population of large cities in Provence, such as Aix, Marseille, and Toulon, meant greater areas of agricultural land were needed. In a region where it rains on average for only 60 days a year, the lack of water became a problem. Although the idea seemed crazy, it gradually became clear that the only solution for engineers was to divert water from the Verdon to the coast. In the 1860s, the Canal du Verdon, also called the Aix Canal, was built. Starting upstream from the village of Canals, its mother branch ends its course 82 kilometers further south, in the fountain of the Rotonde in Aix-en-Provence. To increase its catchment area, the canal has a further 8 branches, allowing water from the Verdon to supply the communes of Aix-en-Provence, Lambesc, Rognes, Saint-Canat, and Venelle, as well as irrigating some 3,000 hectares of new farmland.
Here we are at the Canal du Verdon, built between 1863, 64, and 1875, and thus completed under Napoleon III. It's a remarkable achievement, a feat of great complexity, since it entailed digging out the rock with a crowbar to build aqueducts and walls to prevent the water surging back into the Verdon.
In all, it required almost 2,900 structures to be built in fewer than 20 years. The length of all the channels combined is more than 450 kilometers, the distance between Los Angeles and Las Vegas. It made the Canal du Verdon one of the largest water transportation structures built since Roman times.
This is one of the Canal du Verdon tunnels. At a little over 200 meters, it seems impressively long, but it's actually small since some of the tunnels are more than 5 kilometers in length.
The objective was to be able to transport up to 6 cubic meters of water every second, the equivalent of 2,400 bathtubs per minute.
Here we see the water level at that time. Limescale on the walls has changed the color, so you can see that the water level was almost up to the ceiling. And I'm whispering every line because I'm doing like he is.
The size and complexity of the terrain it crosses made construction of the Canal du Verdon a real technical challenge for engineers, who did not have the benefit of modern tools for alignment or drilling. Work began near Canals with the construction of a 13-meter-high intake dam. The canal then had to wend its way across the Verdon Gorge over a distance of 8 kilometers. To achieve this, the architectural complex alternates between open-air watercourses and underground tunnels, between conduits dug into cliffs and maintained by thick retaining walls, or sections built into the valleys. Over the entire length of the canal, no less than 81 tunnels had to be dug, a total length of almost 20 kilometers. Added to that were forged large siphons, 66 aqueducts, and several aqueduct bridges. Of these constructions, one of the most astonishing is undoubtedly the Calèche Aqueduct, located near Aix-en-Provence. It may not be very high, standing at only 9 meters, the size of a small 4-story building, but its length is impressive. It stretches over 1 kilometer and 115 meters, and includes 146 6-meter arches. Alongside the Canal du Verdon, during its construction, a pathway called the Sentier de Garde Canal was also built. It was originally designed to give maintenance workers access to pipes and tunnels along the 8-kilometer crossing of the gorge. It would ensure the structure's longevity for almost 100 years.
In the middle of the 20th century, the demand for water continued to grow, especially in agriculture and industry. So the canal was no longer enough to meet the demand for water. So it was decided to build a new canal, the Canal de Provence, which would take over from the Canal du Verdon.
50 years on, while hikers can still explore some sections of the Canal du Verdon, the tunnels are closed to the public, primarily for safety reasons, but also to guarantee peace and quiet for the bats that have taken up residence there.
This is a Moran de Cappuccini. It's currently hibernating, so we won't disturb it any longer.
But the Canal du Verdon and Canal de Provence only provide a partial answer to the region's water supply problems. In the 20th century, the hardships caused by the record drought of 1895 had not been forgotten. Likewise, the massive damage caused by the Durance floods. Regulating flow while creating the water reserves necessary for human consumption and soil irrigation had become absolutely essential.
From the early 20th century, our ancestors thought of developing the Verdon to create water reservoirs to meet the region's growing needs for drinking water, electricity, and land irrigation.
Driven by a national policy of regional planning, large hydrographic projects were underway all along the Verdon. Among them, the construction of a gigantic artificial water reservoir in the north of the gorge, the Lac de Castillon. 10 kilometers long and 500 hectares wide, it can hold up to 150 million cubic meters of water. The small town of Saint-André-les-Alpes marks the entrance to the lake to the north. To the south is the town of Castellane. To the east, the villages of Saint-Julien-du-Verdon and Angles border the left bank. Before the waters rose, the Verdon initially passed near a small hamlet of a dozen houses, whose name the lake has kept, Castillon. Situated at the foot of a rocky spur, access to the village was along the N202 highway via the Pont Julien Bridge, a stone structure dating from the late 17th century. When the dam was put into operation in 1949, both village and bridge were submerged under 100 meters of water. In order to store all this water, dams had to be constructed downstream. Like a cork, these huge stone arches block the riverbed and regulate the flow.
Constructing a dam like this is a titanic undertaking. The first step is to divert the river. So we build what's called a cofferdam and a temporary diversion tunnel to provide us with a dry site. Once the site is dry, the next stage is to reinforce the base on which the dam will be built. This involves a massive injection of concrete into the rocks and the creation of buttresses that literally anchor the rock to the ground. Then, layer by layer, the dam is built. Castillon is at a point in the valley where the mountain naturally narrows, with two rocky locks that provide ideal conditions for the installation of an arch dam.
The principle of the arch dam is simple. It is a huge wall with a semicircular shape that diverts the pressure exerted by the water onto the sides, towards the cliffs, just as a bridge transfers thrust forces to the ground. But soon after beginning work in Castillon, engineers were faced with a major problem. The rock on the right bank where the dam was to be built showed signs of weakness. The structure might fail to withstand the pressure of the lake upstream. Tunnels were thus dug into the rock, with multiple cores drilled to inject several tons of concrete and solidify the hole. At the foot of the dam, 3 buttresses were built across the ravine. Each is pierced with deep anchor points to allow the insertion of 900 tons of concrete per block. Thanks to this injection network, the Castillon Dam was welded to its rock. No matter the water pressure, the structure is unshakable. And with good reason. In the end, there was as much concrete in the right bank as in the dam itself. But the completion of these injection galleries to make them operational obviously caused a considerable delay in construction. Added to that were the historical and economic uncertainties of the early 20th century.
Construction of the Castillon Dam is a long story. Work began in 1928, but very quickly ran into problems.
The workforce, largely provided by Germany as war reparations, was recalled, abandoning the site following Adolf Hitler's rise to power in the early 1930s. The company in charge of building the structure then went bankrupt. Soon after, the Second World War put a stop to any progress in the work.
In 1946, against the backdrop of growing energy and water requirements, the French government decided to naturalize all the companies working with electrical energy by creating Électricité de France, EDF. And it was EDF that completed the project. The first kilowatt hours were produced in 1948, and the reservoir was full for the first time in 1950.
It took 20 years then for the Castillon Dam to come into operation, as opposed to the usual 4 or 5. But the result is a colossus. An edifice 95 meters high, 200 meters long, 26 meters thick at the base, and 4 at the top. In total, 125,000 cubic meters of concrete, skillfully assembled. Achieving a result like this requires several stages. An arch dam like the one at Castillon is built using piles, whereby concrete blocks are stacked on top of one another. To build the piles, wooden frames are then filled with concrete. Once the concrete has set, a second formwork is erected vertically onto the first, and so forth. When the first pile is high enough, the dam's angle of curvature is recalculated, then the next segment built using the same method. A copper expansion joint ensures a watertight seal between each section.
Associated with this dam is a hydroelectric plant boasting 4 generating units with a capacity of 52 megawatts, providing renewable electricity to about 30,000 people.
But how exactly does hydroelectric production work? Upstream of the dam, halfway between the surface and the bottom, a huge suction nozzle allows water to be drawn from the lake. This water flows through an underground tunnel dug downstream in the cliff to the left of the dam. The liquid then flows through what are called penstocks. These are large pipes with a diameter of 2 meters, dropping almost vertically from, in the case of Castillon, a height of 90 meters. As it passes through the penstocks, the water gathers speed, and its pressure increases until it reaches 9 bars. At the bottom of the penstock, the water supply pipe gradually narrows and wraps itself around the power shaft. This high-pressure water jet then hits the blades of a huge turbine weighing more than 3 tons. This resultant rapid rotation drives the electrical production shaft, which is connected to an alternator. This alternator consists of a rotor on which an electromagnet is installed. The rotor turns inside a fixed stator, lined with copper coils. The magnetic field thus created allows the production of an alternating current. This current is then sent to a transformer installed at the top of the hill, which increases the voltage from 10,000 to 150,000 volts. Overhead, high voltage lines then distribute the current to the operating grid.
A feature of electric energy is that it cannot be stored. It needs to be produced to meet customer needs at all times. The benefit of hydroelectricity is its flexibility. The fact that it can be started up quickly at times of peak consumption, for example, when everyone arrives home in the evening and turns on their heating.
Because they are flexible, reactive, and the electricity they produce is 100% carbon-free, dams like this are essential to the proper functioning of the French electricity grid. Not to mention their very distinctive architecture, which sometimes offers unsuspected benefits. Since 2009, the Castillon Dam has accommodated a unique and monumental installation, the world's largest sundial. Nestled in the hollow of its vault, it covers a total area of 13,000 square meters, the equivalent of 2 football fields.
It was installed in 2009 as part of the International Year of Astronomy. The idea came from Denis Savoie, a famous astronomer, and Roland Lehoucq, an astrophysicist. They were looking for a site to host the largest sundial in the world, and Castillon turned out to be ideal because of its location and sunshine.
In order for it to work, long curved lines have been drawn all over the surface of the dam. Contrary to a classic sundial where the shadow of a stiletto indicates the time, here the function is fulfilled by the ledge of the dam. It is 3 p.m. when the shadow of the cornice becomes tangential to the corresponding hour line. In summer, the sundial can indicate the time from 6 a.m. to 6 p.m. solar time. An unusual facility, but one that in no way overshadows the site's primary function of producing electricity and managing the hydraulic flow of the Verdon.
The Castillon Dam was the first of a series of 5 to be built along the Verdon, with the others completed later. This Verdon chain allows for 180,000 people to be supplied with renewable electricity, the equivalent to the population of New York's Upper East Side.
After the Castillon Dam in 1948, it was the turn of the Chaudin Dam, which came into service in 1952, followed by the Greux Dam in 1967, then the Canals Dam in 1972. 2 years later, the impressive Sainte-Croix Dam was completed. The upshot was that by 1974, the 5 hydroelectric dams of the Verdon were operating together, producing no less than 600 million kilowatt hours per year. That's the annual consumption of a town like Aix-en-Provence.
Provence, as we know it today, was shaped in part by the construction of these large hydraulic dams. It's important to bear in mind that for centuries, Provence lived according to the vagaries of the climate and was much more prone to droughts and floods. The large structures built along the Verdon have helped alleviate these climatic issues, while allowing the region to develop its agriculture, industry, and tourism.
With its turquoise waters, grandiose relief, and vertiginous peaks, the Verdon now attracts more than 4.5 million visitors per year. But such a landscape has to be earned, and getting there has not always been as easy as it seems today.
Access to the Verdon and Old Verdon in the late 19th century was almost non-existent, just mule tracks, so it was very difficult to move around. It took hours on the back of a mule or on foot to make it through this area.
In order to make the Verdon accessible to as many people as possible, the area had to be tamed with patience and skill. As early as 1861, an engineer from Digny named Alphonse Bauderochas imagined the creation of a railway line linking the city of Nice to Digny-les-Bains. The train would stop in the small towns of Puget-Théniers, the medieval village of Entrevaux, and the commune of Hanau, perched in the middle of the mountains. The route then makes a strange loop. At this point, the train has to meet the challenge of crossing the Verdon twice in order to reach Saint-André-les-Alpes. Finally, after crossing the passes through Moriez and Barème, the line ends up in Digny-les-Bains, across the river Bléone. While the project looked promising, it was an extremely complex undertaking.
The difficulty was in crossing the mountains. This was in the late 19th century, so the mechanical resources were not what they are today, and engineers had to be innovative. The valleys had rivers in them which needed to be tamed in order to build the dikes on which the railroad was laid. They also had to avoid expensive farmland. A balance had to be struck between what was technically feasible and potential cost. That's why it took us so long to build.
While the Chemin de Fer de Provence began work on the project in 1888, the line was not fully completed for another 23 years in 1911. It's worth noting that the train link between Nice and Digny-les-Bains has to cover 151 kilometers through rivers and mountains. In all, no less than 1,000 engineering structures were required to make the route possible. In order to adapt to the restrictions of the topography, the engineer in charge of the project also decided to modify the spacing of the rails. In France, the usual distance between two rails is 1 meter and 4.35 centimeters, which gives trains a turning radius of 300 meters. For the Chemin de Fer de Provence, the spacing was reduced to only 1 meter, thus restricting the turning radius to 100 meters. The train can thus negotiate tighter turns and adapt more easily to the relief of certain mountain ridges. With regard to the station, the topography calls for a specific arrangement. The space available does not allow the train to turn around. To allow the locomotive to return in the opposite direction, a swing bridge had to be employed.
The principle is simple. The locomotive is positioned in the center and pushed around. It sounds easy, except the locomotive weighs 60 tons. So for this kind of operation, the most important thing is to ensure that the locomotive is well centered. That way, with 3 people, preferably 4, it can be turned without much trouble.
With a new rail link offered by the Chemin de Fer de Provence and an accompanying road, the Verdon region was gradually becoming more accessible.
It changed everything. Travel times were suddenly very short. Within an hour and a half at most, you could cross the whole region, which seemed unthinkable. Goods used to arrive here by mule, so not much could be transported. Once the railway arrived, the impact of the region was similar to what we see today with globalization. Products manufactured all over France could easily be brought to the Verdon Valley. Previously, that simply hadn't been possible. Likewise, products made here could be exported throughout the country in large volumes, thanks to the railway. So it really did revolutionize the whole economy of the valley.
Between the 19th and 20th centuries, the Verdon underwent a metamorphosis. While the gorge preserved its raw, inaccessible charm, the valleys underwent a degree of remodeling. New access roads and new infrastructures appeared, alongside the creation of huge artificial lakes, transforming a rural, rather austere landscape into a gigantic seaside resort.
The area has changed since the lakes were created. It used to be relatively poor. It was a farming region with sheep, goats, lavender, almond trees, etc. The creation of the lakes brought in tourists, which gradually became a large-scale industry, with tourists coming mainly in summer to vacation here in the sun beside the lake. Most people who come in the summer don't know that the lake is artificial. The beaches here are not fine sand like those in the Mediterranean, but the beige pebbles blend in well with the landscape, giving the impression of a real beach beside a natural lake.
And yet, what looks like a small sea nestled in the mountains is the result of the Verdon region's hydraulic development policies and incessant excavation by backhoe loaders. It's an epic tale that went on for several decades and finally gave birth to the Lac de Sainte-Croix, the fourth largest lake in France. First, a dam was built at the entrance to the Verdon Gorge. This produced an impressive rise in water levels, flooding the entire valley from Moustier-Sainte-Marie to Sainte-Croix de Verdon. The result was a huge artificial lake of 2,200 hectares, 10 kilometers long and 2 kilometers wide. In the initial plans for the project, the envisaged depth of this lake was 100 meters. This meant completely submerging the village of Salles-sur-Verdon, as well as the hamlet of Fontaine-l'Évêque, nestled in the bottom of the valley. The village of Baudouin, located closer to the shore, was to suffer the same fate. Meanwhile, the small town of Sainte-Croix de Verdon would see its land transformed into a swamp and become uninhabitable. It was a colossal project, difficult to execute with far-reaching consequences.
Since the early 20th century, people had heard about dam projects, but the years went by and nothing was done, so no one expected it to happen. Then, in the 1960s, the Sainte-Croix project took off, and we entered a new world. How can you imagine a lake in place of a 1,000-year-old valley? It was a long and slow process, and it wasn't until the compulsory purchase orders kicked in that people suddenly felt it was going to happen.
From then on, the inhabitants of Les Salles and Fontaine-l'Évêque knew that their villages were doomed. But those in Baudouin and Sainte-Croix were still looking for ways to save their villages. They owe their salvation to a rather astonishing topographical feature: a spring gushing out of a rock, the origin of which is unknown.
During the site surveys, the engineers saw this large upsurge of water at Fontaine-l'Évêque. Their concern was to know where it was coming from. They were afraid that it might act like a siphon and make the lake empty itself like a bathtub.
Fontaine-l'Évêque is only the open-air part of a complex underground network called a karstic network, where many seepage points join a main tunnel. On the original plans, the water surface was to be 78 meters above the upsurge. A physical system of communicating vessels would potentially reverse the course of the fountain and siphon the lake. To get around the problem, two solutions were found. The first was to lower the lake level to 85 meters from the 102 initially planned. This means the karstic network would no longer fill up enough for the system of communicating vessels to empty the lake. The second solution was to block the Fontaine-l'Évêque upsurge with an artificial dam, with a system of sluice gates to control the torrent flow. In order to build the dam, a tunnel more than 120 meters long was dug into the hillside overlooking the spring. From this tunnel, two vertical shafts were drilled. A first is fitted with cofferdams to ensure no water passes, with concrete poured in to close off the spring. then the second with diversion pipes to allow the water flow to be regulated by control valves built into the artificial tunnel. In 1971, when the planned lake was finally deemed to be watertight, work on the dam itself could begin. Built in the deep section of the Verdon Gorge, surrounded by cliffs nearly 300 meters high, the Sainte-Croix Arch Dam is set in cavities dug into the walls. It is 133 meters long and 95 meters high. The supporting thickness at its base is 7.5 meters of reinforced concrete. At the top, this thickness is reduced to 3 meters. With only 55,000 cubic meters of reinforced concrete, the structure is designed to withstand the pressure exerted by the 767 million cubic meters of water in the lake. This makes the Sainte-Croix Dam France's reservoir with the highest ratio of useful water storage volume relative to volume of concrete used. Once the construction of the dam was completed, between 1974 and 1975, the area was gradually flooded with water.
It was quite a shock. What used to be a large, fertile valley suddenly became a large lake with a depth of 90 meters. Nowadays, it might not be feasible to flood areas like this, as was the case in the past. Remember, a whole village was destroyed at Les Salles, completely razed to the ground. It was obviously traumatic for the people who lived in those villages. I'm not sure public opinion would be ready to accept such a sacrifice again, because these people really did make a huge sacrifice to give everyone access to water.
To relocate the inhabitants of Salles-sur-Verdon, whose houses were completely swallowed up, a new village had to be entirely rebuilt. Located in the immediate vicinity of the lake, it is still today the newest commune in France. To replace the roads that ran along the bottom of the valley, the huge Sainte-Croix Bridge had to be built. Spanning nearly 300 meters, it connects the right bank with the left, connecting the department of Alpes-de-Haute-Provence with the Var. At the other end of the lake, the historic bridge of Aiguines, now submerged, was replaced by the Galetas Bridge, which spans the Verdon at the exit of the gorge. Some people still talk about a necessary evil, for while these huge dams have been devastating for the valley's inhabitants, they have also transformed a particularly arid region into Europe's largest reservoir of drinking water.
As we always say, water is life. Without water, there's no life. Here we have the largest reserve of drinking water in Europe, right beside us, supplying 110 villages in the Provence region, which is fabulous. So water is a treasure, a resource for the future.
A precious resource that needs to be carefully managed and distributed as fairly as possible between household, agricultural, and industrial uses. It is the Gréau Dam, the last of the 5 dams in the Verdon chain, that allows distribution to be carried out correctly. Located at the exit of the lower gorge, the shape of the structure sets it apart from its predecessors, because this is a gravity dam, not an arch dam.
When you're planning to build a dam, there are several considerations. The imperviousness of the reservoir, the width of the rocky canyon, and the quality of the rock on both sides of the dam. In the case of Gréau, the rocky canyon is very wide, made from a rock that could not take all the force of the water pressure. In such cases, designers generally decide to opt for a gravity dam. That's to say, the weight of the dam will take the force of pressure from the water to spare the rock formations on either side.
In the mid-1960s, no less than 850,000 cubic meters of clay and pebbles were piled up here. The raw materials for an imposing dam 260 meters long at its base and 54 meters high. While the result may seem rather basic, it is in fact a carefully studied and closely monitored construction.
These dams may look old, but they are very modern. The operation of these structures has evolved in parallel with the technology. Today, they're equipped with sensors that allow us to optimize both operations and monitoring of the structure's behavior. We're actually in an underground tunnel beneath the Grey Roux Dam. We're down here carrying out our checks. In fact, a dam lives and moves, responding to the water level, for example. The higher the level, the more pressure the water exerts on the dam, which consequently moves by a few dozen millimeters. So we periodically collect the measurements for leakage, pressure, height of water in the dam, water temperature. It all gives us a picture of how the structure is bearing up.
Because whatever the weather conditions, the structure must never surrender either to the elements or the ravages of time.
The Grey Roux Dam is equipped with a flood spillway, which is a safety element consisting of two 13-meter wide, 10-meter high sluice gates and a chute, which is a little like a water slide and has a very specific role. It channels the water to the bottom of the dam while at the same time dissipating the water's energy and returning it to the river. It can evacuate up to 1,870 cubic meters of water per second, which, to give you some idea of magnitude, is the equivalent of an Olympic swimming pool every 2 seconds.
The aim is to ensure the dam's maximum level is not exceeded, i.e. the height of the reservoir at which the water could no longer be contained. It is also a matter of not aggravating, or preferably mitigating, flood conditions. As well as producing hydroelectric power, EDF's main job is to manage the water resource. Among other things, its teams are responsible for the sustainability of the multiple uses associated with water.
From the outset, the Grey Roux structure was designed for sharing water. From an intake located in the reservoir, through various tunnels and pipes, then through tunnels and pipes, until the water reaches a splitter, well, a fork, where part of the water goes to the Société du Canal de Provence to provide water for drinking, agriculture, and industry, while the rest supplies the hydroelectric power station at Verdon to produce renewable energy.
Located about 10 kilometers from the dam, the Boutre splitter separates the Verdon's water off into two directions for two separate uses. Part of the water is diverted to the Verdon hydroelectric power station and is used to generate electricity. The rest continues its course along the Canal de Provence. Constructed in 1964, it took over from the Canal de Verdon when it became old and obsolete. The Société du Canal de Provence introduced a new large network whose main canals run for 216 kilometers. 146 kilometers of the structure are entirely underground. The water from the Verdon is thus delivered to 110 municipalities in the Bouches-du-Rhône and Var departments, including Aix-en-Provence, Toulon, and most of Marseille. Today, the Canal de Provence provides 40% of Marseille's water requirements. With its 82 dams and local reservoirs, it enables sustainable and efficient regulation of the water supply for the whole of Lower Provence.
At EDF Hydro, we feel we are on a special mission at the crossroads between water and energy, meaning we're both a producer of renewable energy and a water manager. We are managers, not owners. The water does not belong to us. We have to distribute it between various uses: energy, drinking water, industry, tourism. And this public service mission is something we invest in every day to carry it out for many, many years to come.
For millions of years, the Verdon River has shaped not only the landscape, but by extension, the lives of its inhabitants. By successfully harnessing and diverting the force of the torrent, man has been able to drink, feed himself, and even transform water into energy. Constructing the 5 dams along the Verdon has created an incredible drinking water reservoir of 1 billion cubic meters, providing water for more than 2 million people all over the Provence region. The ricochet effect has also transformed the gorges and valleys into one of France's most popular tourist destinations, attracting 4.5 million people every year to stroll along the beaches and pathways. After flood and drought management, this is the new challenge.
The challenges are very much to do with attendance, or even over-attendance. Historically, the people who lived in this valley experienced 2 traumas. One was the invasion of water, and the other was the invasion of tourists.
As an example, at the height of the season, the village of Sainte-Croix, which usually has only 100 inhabitants, sees its population multiply 250-fold.
People who come here come for the sun, the scents, the flavors, and the water. When it's hot, they want to swim, windsurf, and sail, which is pretty good when it's all in the same place.
But the region's popularity has had a heavy impact on the river and its surroundings. To preserve the raw and authentic nature of the landscape, the Verdon Regional Nature Park and its eco-guards work all the year round to raise awareness among the millions of excursionists.
Le gilet, s'il vous plaît. Mettez le gilet, c'est important.
We must preserve the Verdon because it's an exceptional treasure, nature in its rawest state with remarkable fauna and flora. So these sites must be protected. From what? From over-visiting. In the peak season, in summer, the huge numbers of visitors damages the quality of the sites, particularly with regard to waste. With the attendant risk of pollution, the risk of fire. A fire here would destroy the landscape for 20 or 30 years, or even a generation, so it's essential to protect the area.
At the same time, since 1984, the Verdon Gorge has been classified as a natural geological reserve. As well as acting to safeguard animal life in the region, there is a need to carefully preserve the mineral legacy in the area's 200,000 hectares.
The area needs to be preserved precisely because it is a major tourist attraction. If one person picks up a piece of ammonite from time to time, it isn't a problem. But when millions of people are passing through, everything disappears. Having a nature reserve isn't about cosseting people. On the contrary, it's about improving knowledge, educating visitors about protective measures, raising awareness, offering support, helping them enjoy it rather than just promoting rampant tourism. So, unfortunately, yes, you occasionally have to put on your uniform and enforce the regulations. But that doesn't mean writing out tickets every 5 minutes. I don't think I've ever written one.
In the end, this preservation policy is just a logical consequence of the cycle of human presence in the Verdon. After discovering the site and making it accessible, it was necessary to tame a landscape that was as dangerous as it was sumptuous. By creating canals and dams, engineers and architects were able to overcome the torrential aspect of the river, punctuated by periods of drought and flooding, and thus better manage the precious water resources. Today, the Verdon region is an example of sharing, the sacrifices made by the inhabitants of the flooded valleys, allowing millions to enjoy a reliable supply of electricity and drinking water, is a testament to this. For those interested enough to venture beyond the picture postcard scenery and blissful holiday resorts, Europe's largest canyon is a treasure trove of innovative engineering and a shining example of resource sharing.